It's a pleasure to be back here on the 20th anniversary of the HiPEAC Summer School. And so thank you very much for inviting me back. And today I'm going to talk about computer systems in the foundation model era, which is work that I and my students and my colleagues and collaborators at companies have been doing for a while here. So, everybody knows about foundation models. You have to be living under a rock not to have tried out ChatGPT. And the whole idea is you take a huge machine learning model with billions of parameters and you train it with trillions of tokens, and the tokens can come from text or images or audio. And you build these big models like GPT-3 and 4 and Stable Diffusion. And these models have these huge, really impressive capabilities. One of the key models, things that they learn is this idea of in-context learning. And the idea is that now you have this general model that you can adapt using English text, using natural language, right? And so now you can build systems and applications that before the advent of foundation models would have taken you months with many machine learning PhDs. Now you can do it in a matter of days by programming in natural language. It's a tremendous capability. And of course, transforming society and the world in deep ways, and I'm sure you've all played with these models, and probably many of you are doing research using these models. And there's a Center for Foundation Models at Stanford, which is looking at all the ways in which these models are being used to transform society. So, these models, as you know, have impressive capabilities. You can give them buggy code, and they will fix the code for you. Not only will they fix the code, they'll tell you, where you went wrong, and sometimes they, create bugs themselves, but most of the time they're good. And they'll also generate art. You can give a prompt to Stable Diffusion, and it will tell you about. It will generate some artwork. This is a prompt I gave for a picture. It generates a picture of New York City. These models can also be used to predict the structure of proteins in RNA. People in the biology area call the ChatGPT moment of biology when AlphaFold from DeepMind came to the scene. And these kinds of models are being used to design drugs, and they are tremendously capable in advancing scientific discovery in the biology area. So the way in which we've been looking at foundation models is by taking a full stack approach, right? Using many of the ideas that you will be exposed to in the summer school, right? So starting from ML algorithms, thinking about how you use compilers, especially Dataflow compilers, to cast these algorithms into efficient execution in specific architectures like Dataflow architectures, which are optimized for machine learning kinds of algorithms, how you build chips that implement these architectures and combine them with systems. And then we also come full circle and we think about how you can think about the first set of topics as how you build systems for ML, but of course you can also use ML to improve systems, right? And so that's a last topic. So the rest of the talk I'm going to cover each of these different components of the full stack approach to machine learning and systems in the foundation model era. So let's start with ML algorithms, right? As you know, one of the key capabilities, the reasons that these models are so capable is the number of parameters that you have, and the number of parameters in these models has been growing at a rate of about 10 times per year, right? So 1,000-fold in 3 years. This pace may be slowing down for various reasons, but it's certainly completely outpacing Moore's law. And as you increase the size of these models, they become more accurate, right? They can generate better language. They can fold proteins more precisely. But they also get to inflection points where they get more capabilities. So as an example, so if you want the model to explain a joke to you. So the joke is, I tried 10,000 random restarts of my neural network, but I was accused of overfitting. I guess no good seed goes unpunished. So you give this joke to a 1.3 billion model, and it basically repeats the joke. It doesn't really explain what was going on. You give this same joke to a 175 billion parameter model, and it says, well, this joke is about a play on no good deed goes unpunished, right? And so it will explain the joke for you, and these capabilities, happen once you cross certain thresholds. And so, you continue to increase the size of the model. Of course, it takes more compute, right? Because roughly every parameter you add is another 200 teraflops of compute you need. And so there's a massive amount of compute required to continue to increase the size of the models that you want to be able to train and also serve. So, model size is important. It's getting bigger. There's an increase both in the number of parameters and the number of tokens you need to train these models in order to get maximum accuracy. So one question is sort of how should the model be structured as you start to scale it up, right? So traditionally, the idea is that you would build one monolithic big model like GPT-3 and GPT-4, but there's a lot of research going on about how you can combine multiple specialist models together to achieve a similar or better accuracy to one monolithic model. And Colin Raffles has been doing a lot of work in this area. And he's shown that basically not only do you get higher accuracy, of course, because the model's smaller, you can get dramatically better performance in terms of training and inference by going to a set of small models. At SambaNova, which is a company I co-founded, we're also looking at this idea. We call it composition of experts. The idea is to take lots of small, relatively small models, 8 to 70 billion parameter models, and specialize them for various tasks, and then have another model as a router which decides, given a prompt, which model should actually respond. And this shows that you get performance which is as good as GPT-4, roughly using this technique. So the idea then is that traditionally we've had these large monolithic models, but in the future we can expect to see a collection of diverse specialist models being combined, and the advantage of this is now the combined model, so the composition model is easier to train and much cheaper to serve. So at the core of all of these language models is the idea of a transformer, right? So the transformer is this algorithm that learns the relationship between different tokens in a stream, right? Or in a sentence, or different words in a sentence. So it knows the difference between the dog did not cross the street because it was too scared, knows that it refers to dog, as opposed to the second sentence where the dog did not cross the street because it was too busy, it refers to street. And so the key mechanism in the transformer is a set of decoder blocks which are implemented using the attention algorithm, right? And the attention algorithm, is this mechanism for learning the relationship between and the context between the different tokens in the sequence. Inside attention, you've got these three key matrices, Q, K, and V, which basically correspond to queries, keys, and values. And the dimension of these matrices is set by the sequence length of the token that you are given as the input token. And so the dimension is going to be a square. It's going to be quadratic versus the sequence length. And so as you scale up the size of your sequence, of course, both your compute and your memory size is going up quadratically, corresponding to the increase in sequence length. And so what you'd like to do, of course, is deal with be able to analyze and generate very long sequences, right? There are a lot of benefits to long sequences. First of all, you'd be able to work with very long text documents, such as whole books or plays or long legal documents, and be able to both understand and generate long texts. You can also, of course, think about a vision transformer, and the vision transformer would be taking an image and treating it as a sequence of tokens to be analyzed. And so, of course, the more pixels you have in your image, the higher resolution, the more information you've got, the longer the sequence length required to analyze the higher resolution image. If you could deal with sequences on the order of millions of tokens, then you could analyze DNA, right? So it would open up all kinds of capabilities if you could handle very long sequences. If you could handle long sequences, you could deal with video. And so there are a number of things that you want to be able to do and use these machine learning models for that require, increasingly long sequence length. But as I said, fundamentally the problem is that attention mechanism, this key mechanism that is used in these models, is quadratic in its compute and its size, right? So if you look at the attention algorithm, right? So it's a sequence of operations, matrix multiply, dropout, softmax. And so when you get to operations like mask, softmax, and dropout, you're not doing too much computation. But between each of these steps, you are moving data that is, the quadratic in the sequence length, right? And so if you implement attention in a naive manner, right, on a GPU, for example, then each of these kernels will create data that has to move between the GPU and the high bandwidth memory, right? And so fundamentally what happens is that your performance is then going to be limited by the bandwidth between your GPU and your HBM, right? And of course, as you increase the sequence length, things are going to get worse, right? So, if you give this problem to a parallel computing person, right? Or I teach a class in parallel computing, and we know that one of the key techniques for improving locality and decreasing memory bandwidth is to use fusion, right? To fuse multiple kernels together, right? And so, for instance, what you'd like to do, of course, is fuse all of the kernels associated with attention into a single kernel. But the problem is, of course, you would still have too much data to fit within the memory of the GPU, and so what you need to do is then, of course, tile the computation. So you compute on tiles of data that fit within the memory confines of the GPU. And so this combination of fusion and tiling, these classical parallel computing performance optimization techniques will result in an algorithm called FlashAttention. So the one wrinkle is that there is this softmax, which requires more than one tile of data in order to compute. You need the whole row, and so you need to come up with a way of dealing with that. And so you combine that insight with this fundamental idea of fusion and tiling, and you come up with FlashAttention, and FlashAttention dramatically improves both performance, and so the FlashAttention was the first implementation. FlashAttention 2 was an implementation that was kind of optimized for the idiosyncrasies of the GPU, the warps, and making sure that everything was balanced so that you got maximum performance and you use the tensor cores most effectively. And you see dramatic improvement in performance over kind of a naive implementation in PyTorch. 6 to 10x speed up and dramatic reduction in the amount of memory which comes from tiling. So you can come up with this custom CUDA kernel that implements FlashAttention, and you get a dramatic improvement in performance. Okay, but are we done? Can we do better? Right? So we still have this quadratic dependence on sequence length, and the question is, can we make it linear or log n? And so that is the idea behind what are called the state space ideas, right? So you basically take ideas from signal processing to implement the attention mechanism. And it turns out that you can make it work, and you can improve what's called perplexity. So you see perplexity is a measure of how predictable the language is, so it's a measure of goodness. And some of these subquadratic algorithms like Mamba and Based are actually better in terms of perplexity compared to attention, right? However, when it comes to actually implementing applications on top of these attention mechanisms, turns out that attention is still the winner, still better, right? So the jury's out. We're not done yet for the subquadratic ideas, but there's hope that we will be able to come up with ways that don't require you to do traditional attention. And it turns out that then the compute you need is different, right? You need FFTs, you need scan, you need kinds of operations for which GPUs aren't necessarily optimized for. And so, part of the, what might be limiting what we can do with these subquadratic ideas will be sort of how the architectures that we use to accelerate ML algorithms are implemented, and what sorts of limitations they have. Okay. Sparsity is another idea, of course, for reducing the amount of computation and memory. And again, this is a trade-off between, how efficiently can you do the computation, and what is the net accuracy of the model that you train. And so so there's this tension, right? So all kinds of ideas for sparsity, but either they impact the accuracy too much, or they're not efficient to run on an accelerator like a GPU or something like this. And so the idea of using monarch matrices is the idea of basically blocking. You don't want unstructured sparsity because you can't compute efficiently with unstructured sparsity. What you want is block sparsity, and if you use block sparsity, you can now show that you can get a model that is both, accurate, or just as accurate as you would have with a dense computation, and also the block sparsity is something that can be run efficiently on an accelerator. Okay, the last point I want to make about ML algorithms is that ML algorithms are data flow, right? So if you look at the high-level frameworks like PyTorch or TensorFlow used to develop these algorithms, what you'll get out of them is a data flow graph where the nodes of the graph will be the kernel operations, matrix multiply, convolution, pooling, and the data that's passed between the kernels will be tensor data, right? And so you've got this data flow graph, and so that's the way to think about ML models, right? So what are the implications for ML systems? Well, we need to be able to do compute for very large models with hundreds of billions or trillions of parameters. We want to be able to deal with long sequence lengths. We need to do this energy efficiently because we know that compute today is limited by energy. All right, so we need energy efficient compute. We need to take advantage of irregularity and sparsity because that is the direction that the ML algorithms are moving, and we need architectures that can exploit that efficiently. And lastly, data flow graphs is a natural execution mode for ML algorithms, and so that is something that we should think about how to execute efficiently. All right, so that brings us to data flow compilers, right? So if data flow is what the ML algorithms are naturally expressed, let's think about how to take that data flow and optimize it, right? And you're going to do that with a compiler, right? So you can start with these domain-specific languages, right? Like TensorFlow, like PyTorch, which give you this data flow graph of machine learning operators, right? Turns out that we did a lot of, around 2008, when I first taught at the summer school, I started work with Martin Odersky at EPFL on the whole idea of domain-specific languages, right? So we built this whole idea of domain-specific language compilers, and at the core of those compilers was this idea of parallel patterns as the IR. So parallel patterns you're all familiar with, map, zip, reduce, flat map, group by, where you are working on collections, arrays, tables, tensors. And so these parallel patterns tell you about both the data access patterns and the parallelism, right? The key components that you need to think about and optimize for when thinking about parallel computation, right? And so we found out, of course, that we could take ML abstractions and convert them to a hierarchical parallel pattern representation, right? And then you could also take, so you do it with dense linear algebra, sparse linear algebra, relational algebra, graphs. Lots of things could be represented as this hierarchical parallel pattern mechanism. And then you could take that parallel pattern representation and do optimizations that parallel computer people like to do, fusion, tiling, and this idea called meta-pipelining, where you can think of this as hierarchical pipelining, so you're pipelining at multiple levels in the graph. And once you do that, then you can generate something which is pretty close to a hardware representation. And we represented this in another IR representation called spatial. And by the way, for those of you who like do programming languages, all of this was represented in Scala as embedded domain-specific languages. It was a really cool set of work that we did. And so spatial was this representation that for what we call hierarchical data flow graph of pipelines. And just to give you an example here, this is dot product, right? Kind of the core of machine learning. And the key elements of spatial are this notion of an explicit memory hierarchy, so that you specify where the data structures go, and also explicit movement of data. So you as the programmer get to say when data is moved from SRAM to DRAM, for example. And then, of course, the computation is expressed in terms of parallel patterns, map, reduce, group by, and the like. Okay? So you've got this data flow representation at multiple levels. You've got something that is close to hardware. Let's think about how you might execute that in hardware. So the first thing we tried is, well, let's try and map it to an FPGA. And this was really painful. And so after thinking a lot about compilers, I said, well, maybe it's time to put back my architecture hat and come up with an architecture which is actually a good match for this hierarchical data flow pipeline representation that was described in spatial. And so what we came up with was a architecture we call plasticine, right? So many of you may be you're European, so maybe you played with plasticine as a kid, right? So the nice thing about plasticine, if you talk to Americans, they say, I don't know about plasticine, but I know about Play-Doh. So Play-Doh is flour and water based, so it hardens, right? And so the great thing about plasticine is oil based. It never hardens, right? So you can always change it. And so that's the nature of this architecture. You can adapt it to the algorithm using spatial, and the key components are these reconfigurable SIMD pipelines and distributed scratch pads. So you've got the pattern compute units, the reconfigurable SIMD pipelines, and the pattern memory units, which are these distributed scratch pads, and then a way of connecting them together. In the research prototype, it was statically programmed. In the commercial implementation, it was dynamically programmed switches. Okay, Raghu and Yahtzee were kind of the key people there. So soon after we came up with the idea, it worked so well, we said, this is the basis for a company, right? And so we founded SambaNova Systems. Rodrigo Liang is the CEO, and Chris, my co-founder, also at Stanford. And this is the latest chip. I think I might have one. I can pass it around so you can take a look at it. Where is it? Make sure I get it back, but I'll pass it around. And so this is the latest chip. It's called the SN40L. And it's 5 nanometer TSMC, 100 billion transistors, over 1,000 RDU cores, which is a kind of a combo of the pattern compute unit and the pattern memory unit, 800 teraflops. But the really interesting thing is the memory hierarchy, right? So it's got a lot of memory on chip, half a gigabyte, of course HBM off chip, but also directly connected to DDR, high capacity memory. And you'll see that this is an important aspect of the capability of the systems you can build with this, right? So let's dive a little details. We have some architects in the room, so let me just tell you a little bit about the pattern compute unit. So the pattern compute unit is this configurable SIMD data path that can be configured as a pipeline or as a systolic array, because of course you have to be able to do matrix multiply efficiently, and systolic arrays are the most efficient way of doing that. Handles a bunch of different data types, has these programmable counters for doing looping, right? So no explicit, branches, because that's wasteful, right? So a bunch, those of you who think about DSPs, you take a page from that book about how to do computation. And then the pattern memory unit, right, is a banked set of SRAM arrays that have very sophisticated address mechanisms, right? So you can address the tensors in all sorts of different ways to allow you to do all of the tensor access data. And they also have a data alignment unit that is used for tensor layout transformations like transpose, right? So it's a combination of sophisticated addressing modes, and the data transformation capability allows you to be able to implement these data flow graphs from ML very efficiently. Okay? So here's an example, right? This is softmax, right? So softmax, you can represent it as parallel patterns, and the intermediate XMR, these are tensors, right? These tensors, of course, get put into the PMU memories, and then you can lay out the data flow as in space, right? And so the result is that you get the ability to change the amount of parallelism that you exploit in the different kernels and make sure that data flows as efficiently as possible. So you can improve FlashAttention, right? So you can take the FlashAttention, and not only can you do the fusion and tiling, but you can also do the pipelining, right? So that you now can get multiple operations going on at the same time. And this is called this meta pipelining or streaming data flow. That gives you even added performance and keeps all the elements of the chip active all the time. So as an example of sort of what capabilities you can get by doing this, let's look at a more detailed example of attention from the Llama 3 decoder, right? So this is a Llama 3 decoder. It's somewhat simplified, right? So one way to execute this, as I said, is one kernel at a time. We said that this is inefficient, but you can do it. And if you do it on the SN40L with BF16, you generate tokens at 150 tokens per second. But because you're not using that much memory on chip, you can fit the only memory you need. You can do it in less than 50 megabytes, right? But the problem is, of course, every time you invoke another kernel, you have overheads, right? So you have overheads in terms of data movement and overheads in terms of kernel invocation, right? So then you say, okay, I know how to fix that. I'm going to do FlashAttention. So FlashAttention is something that you could do, and now you're going to get higher operation intensity because you're not moving data back and forth between the accelerator and the HBM. And you get rid of some of the kernel call overhead, and so your speed improves. And you go to 300 tokens per second, and you're still using less than 50 megabytes of data on chip. Okay, what if you could put all of the decoder into a single kernel, right? So the whole decoder fits in a single kernel. You get very high operation intensity. You get no kernel call overhead, and the Dataflow compiler that we developed at SambaNova can do this automatically, right? So you need some hints saying what you want to fuse, but the rest gets done, and now you get to 600 tokens per second, but you need a lot more memory because, of course, you're keeping all of that data on chip, okay? So you need 400 megabytes, right? So this is why GPUs can't do it, because they don't have enough memory to be able to do this kind of fusion on chip. And they also don't have sophisticated enough addressing modes in the tensor memory accelerator, which is something that was introduced into H100. You can't do quite the same sorts of capabilities that the PMU can do. All right? So what if you want even more performance, and you take advantage of tensor parallelism, and you go beyond 8 sockets, and you go to 16 sockets, and then you get to 1,000 tokens per second, right? Which is about 8.8 times faster. This is something that artificial analysis did a evaluation and showed that that we were like 8.8 times faster than Llama 3 running on other providers like GPUs. Okay, so this is the benefit of doing that. If you want to try it out, you can go to fast.snova.ai. You can try it out. So what's the future of these sort of ML inference? Well, there's the whole idea of agentic AI, where you've got multiple models being combined, small and large models, specialized and more general models, in some sort of computational flow that gets defined by the user. And so you've got complex chains of interaction, and what you want is very fast token generation, because you're not the result of the tokens are not being consumed by a person, they're being consumed by another model, right? And so you want things to be very efficient, and you want to be able to switch between the models very efficiently. And so what you can do then with a 3-tier memory is that you can hold multiple models in the DRAM and then switch between them very efficiently with very low overhead. So this is just an example of the time to generate 20 tokens. As I said, we're already faster due to the Dataflow implementation, but then once you get past 570B experts, now the GPU is having to go to the host to get the data, and then of course you've got much lower bandwidth between the host and the GPU, but on the RDU you've got all the high capacity memory, which allows you to have the multiple models. Okay, so what's the future of reconfigurable data flow? Well, so we know the models are getting more irregular. We've got you're making decisions based on, should I go to model A or model B? Should I take a segment of one model or the other? You've got multiple different size batches come in with different sequence lengths, and you need to be able to adapt to that. You've got sparsity, so you need more capabilities. And so this is the idea of Dataflow threads. This is a paper we published fairly recently. And the idea of Dataflow threads is to turn control flow into data flow, right? So Yogi Berra, who was a coach, an Italian-American coach, baseball coach, said, when you get to a fork in the road, take it. And so that's what this model does. It goes both ways at the same time, and it can overcome a bunch of limitations that in existing models. The work that we're also doing going forward is to think about how you go from static reconfigurable data flow to dynamic reconfigurable data flow, right? You can think about the evolution of processes from static scheduling to dynamic scheduling. That's what we're trying to do here. And you see, you've got the computation elements of intermediate representation we call streaming tensor programs. There are only 4 computational components, but there are lots of data reshape components, right? And also elements, components for dealing with control flow. All right, so I talked about, how to improve ML using different kinds of systems mechanisms. I talked about using compilers to optimize the data flow. I've talked about hardware implementations of data flow using architectures like reconfigurable data flow. Now let me say a few words about ML for systems, in particular real-time ML. All right, so the idea is, can you apply ML ideas to traditional systems areas like networking? And in this particular example, intrusion detection for cybersecurity, right? So the idea is you've got a bunch of packets that are coming in, some of which can be malicious, right? And so first of all, you extract some features such as, the timestamps, the packet size, and you feed them to a pre-trained ML model that you've tried that will do classification as to, what whether the packet is malicious or benign, right? And so you run the packets through the ML model, and if it determines that the packet is malicious, then it drops it, and otherwise it keeps it, right? And so this is the idea, and you'd like to do this at the rate at which the packets are coming into your network, at line rate, right? So in order for that to happen, then the model that you use has to be something that you can run really quickly. So it can't be a full foundation model, because there's no way that you could keep up with, a 40 gigabit input stream. All right, so small specialized in-network models are fast, but you'd like the power of a foundation model of a, 100 billion parameter foundation model, because it would be much more accurate and it'd be able to adapt to changes in the traffic, right? And so you can have fast and not very accurate, or you can have something that can't keep up with line rate and be accurate. And so the question is, can we eat it, have our cake and eat it, right? Can we be both fast and accurate? And the way to do that is to think about how we could combine forces between the small, fast model and the much larger, slower model, right? And we could have the slower model retrain the fast model online, right? So you could basically sample some of the data that the small model is seeing, and then retrain the model so that it would be more accurate, right? So the large models guide the small model, and both, to achieve both speed and accuracy at the same time, right? So this is work that we recently published, in fact, last week at OSDI. It's called Caravan. It's called the name of the paper is Practical Online Learning in Network ML Models and Labeling Agents. And it began with work that we developed under a project called Taurus to think about how we put machine learning into the network at line rate, right? So we took ideas from Reconfigurable Dataflow and we put them in a switch to accelerate ML. But now the question is, okay, how accurate are those models, right? And so this is the test bed that we developed. We have a Tofino software-defined network switch, and then we have an FPGA to implement the ML acceleration. And the key student is Kai Zhang. Key students are Kai Zhang and Tushar. Mohammed Shabazz is a professor at Purdue and now at Michigan. Okay, so the application is end-to-end intrusion detection. So you've got a data set with millions of packets. You have different types of attacks, 7-layer DNN. And so if you have the small model, of course, the small model was trained on data or attacks it hasn't seen yet. So it starts off, as soon as it sees real data, its accuracy isn't that good, right? And it gets worse as more different kinds of attacks come in. All right? So if you take the small model and you continuously retrain using the large model as data comes in, now you see that when new attacks come in, there's a dip initially, and then the retraining happens, and then the performance or the accuracy as measured by F1 recovers. There are cases where sometimes even the large model fails, right? And it doesn't track the traffic, but more or less the approach of using this continuous retraining works really well. The problem with continuous retraining is it uses a lot of compute capability, right? So what you'd like to do is figure out when you want to retrain, and so that's the idea of Caravan, is to have some way of measuring the accuracy at which your model is performing and figuring out when you need to retrain, and then this dramatically reduces the amount of compute required, but yet it doesn't impact how well the small model tracks the data distribution, the attacks as they come in. And so that's the whole idea of Caravan, is that you can combine small and large models. So you've got this foundation model. It can't run at line rate in the data plane. What you need is a small model, but you need to have that large model inform the small model or retrain the small model, and then the question is, how can you do that as efficiently as possible? Yeah, almost done here. Okay, so Caravan keeps the network ML models up to date with changing traffic dynamics, right? So computing systems in the foundation model is this co-design between ML algorithms, programming languages, and accelerator architectures. And I've given you some examples, but there are lots of different things that you could do. And I'm sure you come up with your own ideas. And not only is there ideas for systems that will improve ML, but there's lots of interesting work to do in using ML to improve systems. So with that, I'd like to thank you for your attention, and I'd be glad to take questions.